Okay, start. Question 2. Sophia was asking me, how do I get the answer south? This is the north, south, east, west. The magnetic field is out of the page. The current is pointing to the east. So you apply your Fleming's left hand rule. Isn't your thumb pointing to the south? Okay. You draw this picture. Question 3. For question 3, right? Andre, yes, he has already answered. The answer is a D. Why? The reason is because the reason is D because the answer is D because the motion. What is this? Why like that? Let me just close the thing again and open again. Sorry. Hey, close the radio. Close. Close the door, please. Okay, so back to this question. The answer is D because the motion of electron is parallel to magnetic field. Okay? The motion is parallel to magnetic field. That's why there's no force. In order for you to experience a force, the current must be non-parallel. Now it's parallel, so there is no force. Okay? It doesn't have to be perpendicular, guys. As long as it's non-parallel, you can always resolve the current such that there is a component perpendicular to the field. Okay? But if the current is parallel, no way, there will be no force. Question 4. You apply your Fleming's left-hand rule. Zixiang, what is your answer? C. C for cat. Let's see whether if it is C. They want a force there. The current is out of the page. So current out of the page. The force is there. So you use your Fleming's left-hand rule. Right. Huh? 1. The magnetic field must be pointing towards C. Okay? The magnetic field must be pointing towards C. So the answer is C. You apply your Fleming's left-hand rule. That's the force. That's the field. Never mind, we shout louder can already.
Question 5.
Straight horizontal wire carries right angle to the magnetic field. And the field is 8 millinewton. Now the wire is rotated such that it is 30 degrees as shown. And the field is half. What is the vertical force? So in the first place, right, we know that F is VIL. And you must make sure that the I is perpendicular to the L. So for the first case number 1, the F is VIL. Okay, that's it. For the second case, the F nu is V over 2, right? Half of it what? The I is still I, the L is still L, but you need to cosine 30 degrees. Why need to cosine? Because I want to make I perpendicular to B. Sorry, this must be perpendicular to B. I read wrongly. Sin 60 or cos 30, I think is the same answer. Sorry? What B? B is magnetic field. Okay, B is magnetic field. Can So we will take the O force over the new force equals to BIL. Here is B over 2 I L cos 30. So actually your B, I, L all cancels. So it's like 8 millinewton over the new force equals to 1 over so your new force I think is 3 point something if I'm not wrong. Say what? What do you say? To make I perpendicular to B. Yeah. To make I perpendicular to B. Okay, so what is the answer? 3.46 if I'm not wrong. Right, Caris? 8 millinewton is according to the question. 8 millinewton. Can So it's 3.46, right, Andre? Hey, press to see what's the answer. Why? Okay. Ziqi say press your calculator lah. Okay. I know. You don't see that she's so like, you know. Hey, sorry, this is being recorded. I think better don't anyhow say. Okay, so the new answer or the new force is definitely weaker. It's definitely weaker than the original force. And how much is the new force? 3.46 millinewton. Can? Okay, let's move on. Timothy, number 5. The key thing in this question, right? Shh. The balance, the thing is when there's no current, the reading is 142. If your current 2 ampere, it 144.6. Okay? What happens if it is 3 ampere but in the opposite direction? These are the important stuff. Okay, obviously when you reverse the direction of current, what happens? Okay, the first thing you write down here, direction of current is reversed. It implies that the force is reversed. Okay, the force is reversed. Definitely the force must be reversed. Okay, so you are expecting the reading definitely to be less than 142 grams. No current is 142. Current flow in XY is 144.6. Now flow in YX, it must be lighter. What? It's like it will make the magnet lighter. Okay, it will make the magnet lighter. Just now the force make the magnet heavier by 2.6 grams, you can see. Right. From 142 become 144.6. The force makes the magnet heavier by 2.6 grams. Now I reverse. We know that the force is directly proportional to the current. You wait first, can or not? So F1 over F2 will be I1 over I2. Correct? Because the B is unchanged, the L is unchanged. So the original force, first force is about 2.2 grams, 2.6 grams. .9 grams. Okay? The new force will make the thing change by 3.9 grams. So the reading will be 142 minus 3.9, which is 138.1 grams. That's the new reading. You must know why it becomes lighter instead of becoming heavier. Because if I reverse the direction of the force, just now the force pushed the magnet down. That's why it's 142 become 144.6. Now I reverse the current. The force is definitely going to lift the magnet up. How much? 3.9 grams. Original 2 ampere current produce an additional force of 2.6 grams. 3 ampere will be 3.9, directly proportional. Okay? Can or not? Okay, guys. Carries. Low. Don't sleep. Never mind. Your classmate will be listening to what you say. Yeah, actually you don't really care, right? Okay, next question. 7.
Teacher beat me. Teacher stop.
Okay, question 7. They ask for the force by Y. They are interested in by Y. We know that X and Y attract each other. That's by X. Then by Z is a repulsion. Okay? So you can see that the force on Y is to the left. Because Y is attracted by X. But Y also repelled by Z. So one attract there, one repel there, so you will go there, to the left. Okay? Y and X attract, but Y and Z repel. But we are not really interested in X and Z. We are only focusing on Y. Can? So the answer is to the left. Come again? Yesterday we spent half an hour to do Y attract. Same direction, current, attract. Opposite direction, repel. And yesterday we go behind the reason. I asked you to do one time, attract, one time, repel one. Now you ask me why attract. We spent half an hour on that yesterday. Please, look back at what you wrote. He has integrity. Not like you. You will only say what is true. Number 8. Okay, guys, two long straight wire carry current of magnitude 1 ampere and 2 ampere respectively. Both current are pointing northward. Draw a diagram to show the direction and the relative magnitude of the forces on each wire. Okay, you have to know that the wire, right, they both carry to the current to the north. Okay, one is 1 ampere, one is 2 ampere. Right, we know that they will attract each other, definitely. Will the force of attraction be different on each other? Will the 1 ampere attract the 2 ampere more, or will the 2 ampere attract the 1 ampere more, or it's the same? Sophia, you must sleep more and drink more water. You have a lot of pimple recently. Stress. No. The answer is they attract each other with the same force. Because it's Newton's third law. Action, reaction, pair. The force of attraction between the two wires are a pair. Action, reaction, third law. Newton's third law. Why? Okay, let's look at the solution. I'm going to explain using the solution. Check it out. Yes, you are right. So, this is wire 1, wire 2. Okay, we will draw. Remember yesterday I draw the thing, but now we're going to put in numbers. This region, the magnetic field is into the page, due to 1. Okay, we call it B1. Okay, B1, right, is given as mu naught 1 ampere or I1 over 2 pi A. That's B1. And then here is magnetic field due to okay. Benjamin just reach, okay?
What are you recording for? What's this so special? Oh.
Okay, guys, shh. So you can see that the force on Hey, sit down. The force F1 is BIL, but it's the B due to wire 2. It's the B due to wire 2, its own current times L. You can see I sum inside. And realize that both numbers are the same. Please jot down this. Okay, if you want to find a force due to one of the wire, field due to one of the wire, you have to find the field due to this guy. But the force, right, BIL, the B must be the B due to other people's B. I repeat again, when you use BIL, the B must be other people's B. Like if you want to find a force on wire 2, you use the current in wire 2, but the magnetic field due to wire 1.
So what's the
B2 lah.
Why?
Because I want to find the force on wire 1.
So the B is
I want to find the force on wire 1, I have to use the magnetic field of wire 2. He must be sitting in other people's magnetic field to find the force. He cannot be sitting in his own magnetic field. No way. And by the way, please also write. Actually, they are. Benjamin Pang, are you feeling okay? I won't say anything bad about you because I'm recording it.
how come the magnetic field has
He already tried that just now. Yeah, I already injured Zi Xiang already just now. I beat him up just now. That's what he wants to say. Let's move on. Shh. Question 8, please jot down the answers. Hurry up. Okay, are we ready? Next question. Jeron, number 9. Can Okay, let's move on. Question 9. Question 9, the answer is Z and Y are out of the page. W and these are into the page. Why is that so? You just use your right hand grip. You see, I want the resultant field to the left, right. This one goes out, comes in. This one goes out, comes in. It's like you grip it in this way. It's just like a cross-sectional view of a solenoid. It goes out, comes in. Right, remember the picture of how the solenoid looks like. The top view or the cross view of a solenoid is like that. Can you remember? Yesterday we did this. And the magnetic field inside is like that. Yeah, sorry. Yeah, it's like that, right? So it's the same. This is just like part of a solenoid. So the answer in Y and X are, Z and Y are out of the page. W and X are into the page. A is the answer. Using the solenoid. Okay, if you not sure why it is like that, Question 9, you can take a look at, here. At the summary page. There, can see? Can see, right? These are all the crosses. Okay, this is the top view of a solenoid. So what you see just now is like a solenoid as well. Same. Exactly the same. Can? So that's for 9, huh? Okay, Ziqi. Charlotte, wake up. Charlotte, every time during my lesson, falls asleep. After school, she's very active. Yesterday, I saw her running around in school. Okay, 10. Shh. Hey, this question, right? Timothy, you come and present on the board now. Using the same rule. Timothy, hurry up. Yeah, actually this question is quite straightforward. Just draw 2 things only. You draw on my screen, come. Now. You want to draw on the screen? No lah, draw my face. Outside also, not just inside, please. Draw outside. Yeah, although they say in, I will prefer that you draw outside also. Hey, finish drawing for all the lines lah, friends. Okay, so what Timothy has drawn is this. Yeah. And I was saying that please draw outside as well. Although it's not necessary by the question. Outside, it means like that. He has to try. Because I draw here, people cannot see on the screen. I'm recording the screen, you see. Right, unless you take a video camera, take everything down in the classroom, then it's fine. Okay, next. Draw a line to represent the current carrying conductor that does not experience a field. How? Dim. I don't want any false one. How should I put a current carrying conductor? Parallel, perpendicular, or non-parallel? Or don't draw at all? Don't draw no force, but confirm one. Also no marks. No, that's the magnetic field. Yes, you draw any current carrying conductor, okay, as long as it's like that. It carries current here. Like that can already. You know what I'm drawing? That's a current carrying conductor and that's the direction of the current. As long as current parallel, or you can say anti-parallel. Anti-parallel means opposite direction. Then can already. BIL. I must make the I perpendicular to the B. If it is parallel, you cannot resolve. Any component perpendicular, no way. But if it is non-parallel, there is always a component that is perpendicular. Okay, ma? Cannot do. No force. Or you want that way also can. Doesn't. As long as it's parallel. Both also can. Both also can. Same direction, parallel or anti-parallel. Anti-parallel means opposite. 1 point left, 1 point right. Parallel means one point left, the other point left.
So can you explain?
Explain which one.
Why as long as current parallel, then the magnetic field does not experience something?
When you use the formula BIL, you must always make sure that the I is perpendicular to the B.
So don't you care about this?
But if it is parallel, there will be no component of the current perpendicular to the B. Yeah? Let's move on. Next one. 11. Yeah. The key thing is parallel. Okay, let's move on. 11. Okay, 11 we do later. We do 12 first. Shh. A charged particle is moving in the field and they say it's out of the plane. The B field is out of the page. Sorry? Never mind. The key thing is right. We know that this is the center of the circle. Okay, I'm going to tell you that the force is towards here. So now I would like you to tell me whether the answer is a positive charge or is it a negative charge. Use your Fleming's left hand rule, determine whether it's a positive charge or negative charge. Remember, current and positive charge, same direction. Current and negative charge, opposite direction. Yes, 11 we will go do it later. I say 1 because that's the center of the circle. Yes, that's why it's going in a circular motion. The force is going towards the center of the circle. So Ashton, is the current positive or negative charge? I apply Fleming's left hand rule. See, current, don't know. Field, out of the page. Force here. So you can see that the current is actually this direction. Right? And the charged particle is going in here also. The current and the charged particle are going in the same direction. So what is this telling you about the charge? Yes. The current, if you apply a Fleming's left hand rule, right, the current is here. Right. So since motion of charged particle is in same direction as I, the particle, mass. Okay? Positive. Motion. Out of the page. The question says so. No, that's the center of the circle. Yeah. For those who missed out this lesson, you can always catch it online. Mine is Chia MSN. Yes. If it is a circular motion, the force is always towards the center. Remember that. You see when you cough just now, Charlotte is like, oh. You never see Charlotte's reaction just now. Okay, sorry. Okay, 13. Okay, this question, right, only wants you to sketch. We have modified it. So it's an electron, guys. C and D both can. Actually, there was another option, but we removed the option. It's negative charge. So if you apply a Fleming's left-hand rule, the current is here, which means that the force is here. Right? Because if the electron go down, means the current goes up. So the force must be to the left. You apply a Fleming's left-hand rule. So the electron's path will be such that I will use a blue color. It will be such. Anything curved downwards is fine. Sorry, I draw again. Maybe something like that. Anything curved downward is fine. Sorry? Okay, Charlotte doesn't like this. Then you curve down. Can? Like that. Is this okay with you? Cindy Mondi. The fan. Next one. 14. YouTube. It's YouTube. What's wrong? Assuming that liquid sodium. Okay, you all read first. Okay, I can give you a hint. I would like you to calculate it yourself. Resistance is rho L over A. But remember, the L is always parallel to current. The A is always perpendicular to current. Hope you remember this when we do the chapter. So the rho, based on the question, is the resistivity. The L is 2 cm or 0.02 meter. The A is 0.05 times 0.05. Okay? Take note of that. You can see that from the picture. This is the L. This is the L. Because the current flows in this way. And the area is this. Sorry? Area 0.05 times 0.05? I just shade the area, right? Is it? Oh, I'm sorry. Sorry. Felicia is correct. No, Jolene is correct. Thanks. What new one? Yeah. So you can work out the answer yourself. And of course the PD, right, for part 2. It will be V is IR. The I is 50 ampere times your R. Okay, you can get the answer already. Okay, not? You better sit here, you better sit properly, Cindy. draining. Okay, the next question. The force is applied. State and explain the direction. The direction is, obviously, is to the left by Fleming's. Okay, the reason is Fleming's left hand rule. Good enough. I think you got. I said left just now. You are the one who shouted right. Calculate the magnitude. The B times the I that was found in just now times the L. The I was found in A part 2 already. Hey, sorry, the I was 50 ampere. What am I talking about? So that's the force. Can? What? Fleming's left hand rule is the accepted explanation. Yes. The force is to the left. Okay, let's move on. Move back to the last question. Can Okay, determine the total length of the wire in a coil. Okay, for this question, right? They have 1,500 turns. And they have the radius is 22. Yes, so it is the circumference of one round. That was 1,005. Hey, sorry. Pi d, okay, so that is the total length of the wire. That's for number 1. You do it yourself. Okay, instead of me giving you the numerical answer, I'm going to help you with the working. Please go through the steps yourself. The total resistance, R is rho L over A. The length is the answer in part 1. Okay? Can That's the total resistance in the coil. And of course part 3. Part 3 is a free mark. You just use like I is V over R. Okay? These are the answers. Numerical. Go and work it out yourself. Sophia, are you okay so far? No problem, right? All this. Okay, next. Draw the pattern of the magnetic field within and around the solenoid. Use the arrow to show the direction. Okay, please refer to summary in notes. They have the picture. This one, you draw yourself. Next. Okay, the current balance again. So it's very obvious that there's a force here, and usually we'll put something heavy here. Okay, it's going to be something like that. And then it will balance like a seesaw. F times the BC must be equals to the mg times BA. Right? Balance one. Okay, when in use, there is a turning effect on the stiff wire caused by the current in CD. Explain why the current in CD causes the turning effect. Okay, this answer right is 3 marks. First thing is you must use that's the first mark. This will cause a moment about dE, which is the turning effect. So first thing you apply using Fleming's left hand rule, you must have a force, and then this force multiplied by the perpendicular distance from the pivot. This will cause a turning or a moment about the pivot dE. Hey, why are you wearing shorts in class? You didn't hear enough PE? Yes, Jerome. CD and field. For the field, the F, the horizontal line disappeared. And the L also disappeared. Wait ah. Write too fast. The field, this word is the field. Where is Troy, by the way? Oh, 7 people not in class today. So bad. Your class is what? Got 14S1 ah? 18 ah? Wow. Okay. Okay, let's move on. The current is parallel to the B field, so no force. Can? No force means parallel. Okay? Okay, so what is the current in CD? So let's continue. You can see from this picture, CD the current must be flowing from C to D. Because the magnetic field is pointing in this direction. Okay, the current must be here. So to answer this question, you can see that because the magnetic field is pointing this, you apply a Fleming's left hand rule, then you can get the force in that direction. Can see, right? Right. Fleming's left hand rule. You see the picture, the B points to the left, the force is down, the I must be from C to D. The explanation is just by Fleming's left hand rule. Okay, the direction of the current is from C to D. Reason, is by Fleming's left hand rule. And then now, they want you to calculate the magnetic field in the solenoid. So okay, now we have this F, guys. We know that by principle of moment, clockwise equals anti-clockwise. Clockwise is 5. Anti-clockwise is F. But the F, right, you can further speed up into BIL. So you can work out the F first from here. But okay, then you can find the answer. The unit is in Tesla. Can? Okay, guys. Nice, right? Today lesson very efficient. We never talk so much like life skills. You can see how quiet and how efficient our lesson is. Okay, let me